Now that we've done one example involving an if and only if statement we're proving about sets, here's another example. We're proving that X is an element of A if and only if the set containing X is a subset of A for any element X in the universal set. So again, here is some preliminary strategy before we actually write the proof. We have to remember P if and only if Q is a biconditional statement, which means to prove that it's true, we need to show if P then Q and if Q then P. Notice they write it in an interesting way here. If P then Q and if Q then P. This explains why in the previous section you were seeing the implication arrow going in different directions. So then just some terminology that you'll probably see a lot. The two implications, one of them is called the necessity and the other one's called the sufficiency. Usually we just identify them by the direction the arrow is pointing. So we have if X is in A, then the set containing X is a subset of A, and if the set containing X is a subset of A, then X is an element of A. This is the basic structure of what the proof is going to look like. These are direct proofs. We start by assuming the hypothesis of the implication we're trying to prove. We do some stuff. We conclude the conclusion of the implication. And then same thing, but going in the other directions. Start by assuming Q in this case, do some stuff, and then conclude P. So here's how the actual proof would go. It's going to be kind of short, but it's important to talk about the strategy of it ahead of time because it's a little hard to come up with that on your own when this proof stuff is still pretty new. So here is going to be the actual proof. Again, we're indicating we're proving one direction of the biconditional statement first. We're assuming X is an element of A. Then we consider what does that say about the set containing X? Well, we know that that set only has one element, which is X, and we're told that X is an element of A. Remember what subset means. It means every element in this set is in this set, and that's exactly what we just observed. So that's why the set containing X has to be a subset of A. Now, when we do the other direction, the implication going in the other direction, the other half of the biconditional statement, we have to pretend that we started all over again, and now we're assuming the second part. In other words, the Q, or in this particular example, we're assuming that the set containing X is a subset of A. And we're going to write what that means and what that means and what that means until we get to conclude that X is an element of A. So here's how we do it. Well, what does subset mean? It means that every element of the set containing X is also an element of A. But the only element in the set containing X is just X. Not that that matters. The main thing that matters is X is an element of the set containing X. Therefore, it's also an element of A. Thus, X is an element of A.